Okay, now let us come to a projective transformation. Projective transformation. What is also referred to as a homography. Called a homography. Somebody say homography, whatever, it doesn't matter as long as we know what we are saying. Okay, now the goal is like this, right? I'm going to draw. Okay, now let me write down what is the goal. The goal. Okay, why we are doing this? The goal is to relate. Images of a planar scene. Now I'll start with a planar world. Like I told, planar world is actually a nice world. Planar does not mean it has to be fronto-parallel. By fronto-parallel, right, what I really mean is, okay, something like this is a very special case, which is fronto-parallel. So you have a camera, right, whose sensor plane is like that. Okay, let me put it like this so all of you can see. Then this is a fronto-parallel scene. Okay, and the way we normally call right, if this is your sensor plane, think of this as your x coordinate of the sensor. This is your y coordinate, and the one that comes out is just an optical axis of the camera. Okay, that's the way we treat. And the place where these axes are all originating, okay, that is supposed to be the camera center. Okay. Now, so all your light rays, right, are going right through that center now. Okay, so you can imagine a center through which is a pinhole, through which your light rays are going. And obviously, right, you can see that if you, even though from a point so many rays will kind of come out, emanate, but only one ray goes in, which is also the reason why you tend to use a lens, because a pinhole can then, because for a pinhole, if you want enough light, you have to wait for a long time, because right, you don't get all the rays. But if you have a lens, then you can actually bring them all and then focus them, right? But right now, with actually a pinhole model, what it means is we are looking at a scenario like this where I have a camera like this, and the scene could be something. It's a planar world, but now this could be anything. For that matter, this could be something like that, something like that. Fronto-parallel is actually a special situation which we will talk about. Okay, this will be like this. So this is a fronto-parallel. These are all other cases. Okay. Now we are not assuming fronto-parallel here. We are just saying that it's a planar, right? It's just a planar world. So let me write down. Where was I? Yeah. So the goal is to relate, okay, images of a planar scene, taken from two different views, by a linear transformation. Which means you want a matrix, right, to be able to relate by a linear transformation. Okay, that's the goal. Now the way, right, I'm going to draw this diagram, okay, is like this. So I have, let me say that I'm just drawing something. Okay, let's say this is my optical axis, this is my camera plane. So this is like x, y, and then that's my optical axis. And normally the optical axis, we tend to think of this as the z axis. We coincide the optical axis and this is z axis. Okay, so this is your z, and I'll call this the optical axis. All this just for simplicity. Okay, we assume the optical axis to lie along the z, or we assume the z to be along the optical axis. And imagine that right here is a plane. Okay, some plane is out here. Okay, which we are imaging. Okay, we are trying to capture an image of this plane, and let's say there is some point P sitting on that plane, and let me draw a unit normal. Let me draw a unit normal to this plane. Okay, so this is some n, which is a unit normal. Unit normal, and d is the perpendicular distance. Now d, okay, is from here to here. So I mean, how do I show that? So from here to here, right? That's my d, and d really is the perpendicular distance. Is the perpendicular distance of the plane from the camera center. Okay. And then this, let's call this as our O1. Okay, here is where we are originally. Okay, this is the camera center. Camera center. So all your light rays are going to go through that. And then assume that we actually move to some other location O2, just some arbitrary y, let's say some z and some x. Okay, so I've undergone some motion. Here, of course, it should involve translation also, because I'm not sitting right there. If I was sitting right there and if I changed the axis, that would have been a pure rotation. But I'm assuming that I've also rotated, and I've also probably done some translation and arrived at O2. Okay, so what we are asking is the image of this plane when seen from O1, when the camera was at O1, then the image of the same scene when the camera was at O2, assuming that the scene hasn't changed in between. Right? How are these two images kind of related? Can they be related by a simple linear transformation? Okay, that is what we are asking. Okay. Now let us say that suppose, okay, let's go on and suppose the coordinate of point P, right? Point P is some arbitrary point on the plane. Suppose the point P with respect to O1 is x1, what is it, y1, z1. Okay, all in caps. Okay, so which means that this is your scene coordinate. Okay, this is a 3D, this is not the image coordinate, this is with respect to O1. That means that in that world coordinate, okay, where is the P's coordinate is like x1, y1, z1. Okay, now at this point of time, right, when we want to examine what will be the image of this 3D point, right, onto the camera sensor. Okay, when this ray from P hits goes through the camera center and hits the sensor plane. In order to understand that, we should understand what is called a perspective projection model. A projection in a pinhole camera. In a pinhole camera. A perspective projection in a pinhole camera. You must have heard of this, right? But then we'll just see what is its relevance here. Okay, and incidentally, this particular model also holds even if you have a lens, by the way. Okay, which we'll see later. Okay, so that way it's an important thing. So what this means is that suppose we have, let us say that, right, this is our optical axis of the camera. Assume that our sensor plane is sitting somewhere here. Okay, so this is the camera sensor plane. Okay, here is where the image will get formed. Okay, this is your optical axis of the camera, and assume that the camera here is the pinhole through which the rays are going to come, and assume that there is some point in 3D. Okay, suppose, right, this could be your point P, for example, right, this guy, okay, let me draw it a little bigger. So this guy ray comes and hits the sensor plane here, correct, on the image. Now in reality, of course, you should have actually, we should have like x comma y, but I'm just doing it on a page, right? So I can only show one of the coordinates. So imagine that it's like this, right? You will also have a y correspondingly. I'm just going to show x. So from here to here, right, this is your x coordinate for this point, right? And of course, treating, let's say this as your origin. Okay, so and from here to here, okay, is your focal length f. Right? That's the focal length of the camera. And let's say that right, from with respect to this as the center, this guy is, let's say, x, a capital X. Okay, and from here to here, let's say it is at a distance d from the center of the camera, right, which is the aperture or the pinhole. Okay, so here is your 3D point. Okay, this is your 3D scene point. Right, so a point will of course map as a point, but if it's a lens, you can't be sure. It can actually become a circle, but because this is actually a pinhole model, so it's easy. So a point will go as a point. So this ray will travel here, hit it here. Now, just to simplify things, right, instead of looking at the inverted sort of image, what we normally do is we just take the same f on the other side and then examine here, right. So here to here is still x. Whatever is here, I just taken it on this other side. Okay, just to ignore this. This is the inversion. Okay, which you see here. Now, if you simply apply similarity of triangles, so what do you see? So we see that so from here to here is again f, right. So we have kept it. So this was f, this is also f, this is x. So what we see is that x by f, right, which is this angle, is the same as capital X by d, or we see that x is f into fx by d. And similarly, you can show that y will then be fy by d, right. If this guy has a coordinate x comma y, right, x comma y comma d, actually this 3D world coordinate is like x comma y comma d, and this will be some x comma y, which is your image coordinate, right. So your small x and small y are the image coordinates. So where this guy is going to fall. Okay, x equal to this, and then right y is equal to this. So what this also means is that okay, the focal length also, right, enters into the into the equation, and so on. Now, with this, right, I mean, so since we know that here is how this mapping will happen, right, between the image and the scene coordinate, now we can go and write down this kind of a relation, right, between the scene coordinate and the image coordinate. But then unfortunately, if you see here, right, these two are kind of say entangled. If you see the z, right, or now in our case it's like x comma y comma z. I called z as d here. In our case, that point has a coordinate. You see, this guy has a coordinate x comma y comma d. For our p point in general, it was some x1 comma y1 comma z1, right. So our equation would have been, the image coordinate would have been f x1 by z1, and y is equal to f y1 by z1, right. That is what we would have got for p as the image coordinate. Now we want to be able to write up an equation that will relate through a matrix the scene coordinate with our image coordinate, right. That's what we want to write. So in order to write that, what we actually resort to is what are called homogeneous coordinates. I'll talk about what these things mean. We resort to what is called homogeneous coordinates. See, these homogeneous coordinates, just as you see, right, this entire thing, right, that we are doing, which is really a projection of a scene, right. What you are seeing, the image, is simply the projection of a scene onto the image plane, okay, onto the image plane, okay, involves, I mean, right, when you want to analyze this, it involves what is called really a projective geometry. Okay, and just as what Cartesian, okay, let me write this down. So what a Cartesian coordinate, or what the Cartesian coordinates do, for Euclidean geometry, the same is the role of homogeneous coordinates for really a projective geometry. Homogeneous coordinates for a projective geometry. Okay, now our idea is not to go into the complete details, because a projective geometry is a whole subject by itself, projective geometry, but right, we would just like to kind of borrow right important things from there. Now, when you say right, homogeneous coordinate, right, what it actually means is, now the way we write it is, I mean, you can always go kind of back and forth between a homogeneous coordinate and a Cartesian coordinate. Okay, if you have a Cartesian coordinate in an n-dimensional space, a homogeneous coordinate is simply an extension of the Cartesian coordinate to an n+1 dimensional space. It just adds one, say, extra sort of dimension. And why do you do that and why this, that is the reason why I wrote here that why you do this, why you require this homogeneous coordinate. In fact, right, that is how it came actually when, let's say, when these people wanted to explain a projective geometry. And what you can see is that it allows you to go from a homogeneous coordinate to a Cartesian coordinate, and at the same time you can extend a Cartesian coordinate to a homogeneous coordinate by simply adding one more dimension. And it helps when you write the coordinate in the homogeneous form, then this matrix relationship that you are seeking will automatically happen. Okay, how I'll tell you. So in this case, right, we said that x1, which is the image coordinate, x coordinate of that point, is what f x1 by z1, right, for point P. Okay, this I am writing for point P. And then y1 is f y1 by z1, right. This is what we have. Now when you write in a homogeneous form, so what you will do is you will write this as z1 and you will write this as x1 y1 1, or in other words you write this as z1 x1 z1 y1. Okay, now the z should be capital, by the way. Okay, this is not small, it's looking small. So z1 x1 z1 y1 z1 is equal to, now I'll write this equation and then you will see that it makes sense. f0 0 0 f0 0 0 1. This is a 3 cross 3 matrix, and then I'm going to add a 3 cross 4 matrix 0 1 0 0 0 0 1 0, and then I'm going to write down my scene coordinate as x1 y1 z1 1. Okay, just as my image coordinate. Now you see my image coordinate is what, x1 comma y1, right? That's a Cartesian coordinate. Now from the homogeneous I can go to the Cartesian by simply dividing the first two elements by the last. So z1 x1 by z1 is x1, z1 y1 by z1 is y1, right? So I can go from here to the Cartesian by simply dividing the first two coordinates by the last entry. And because I'm in a homogeneous world now, my scene coordinate, I'm going to write it as x1 y1 z1 1, right? I always append this additional 1, right, in order to be able to go from, so which is what I mean by extending by, let's say, one more dimension. So in a simple form, if you had, let's say, x comma y, right, and suppose you wanted to write an homogeneous form, it will become x y1. You can also write it as, zx, zy, z. Okay, that is also fine, because so the entire thing, they're all like x comma y comma 1, because any alpha that you multiply, right, will also have, but that is why this homogeneous, that word comes from that. I mean, x y1 is the same as alpha x alpha y alpha, right? Alpha should not be 0, of course, right? So that is why this homogeneous notion comes. And here, right, so this 3D scene is in a homogeneous form. The image pixels are in a homogeneous form, and you can clearly verify, right? If you multiply these two, what will you get? x1 what is that? y1 z1, right? If you multiply these two guys, and then if you multiply this with f, what will you get? You will get fx1, you will get fy1, you will get z1. On the left you will have z1 x1, you will get z1 y1, you will get z1, right? And you're saying that, right, this is equal to this, correct? And clearly x1 is fx1 by z1, y1 is fy1 by z1, z1 is equal to z1, right? So it's all fine. But then the advantage that you now have is you are able to write a scene coordinate. So in a way this is also represented as the image coordinate being represented as simply a P, a projection matrix. P is not that point P. This is simply a projection matrix multiplying the scene point. Okay, if written in homogeneous form, you can write like that. You can relate a scene coordinate with respect to the image coordinate in a homogeneous form, where this is called really a projection matrix. Okay, this is exactly the reason why we resort to what are called homogeneous coordinates. Okay, now assume that we actually assume that we perform 3D rotations and 3D translations, and of course note that these rotations could be in any arbitrary sequence, and the rotations don't compose, like Rx composed with Ry composed with Rz is not the same as Rx composed with Rz composed with Ry, and so on. Okay, so assume that we perform 3D rotations and 3D translations, of the camera to go from O1 to O2. O1 to O2. Okay, so we've gone from O1 to O2, right, doing right some kind of transformation. And this again, right, we'll write in a homogeneous form as x2. Suppose, okay, now, and suppose, let's say, and suppose the coordinate of P with respect to O2 now, because we have gone from, now we have moved the camera now, with respect to O2 is x2, y2, z2. Okay, since we have moved now from O1 to O2. So now what we can do is, right, we can relate x2, y2, z2 1, which is actually writing the world the scene coordinate in a homogeneous form. This I can write as a 3 cross 3 matrix R, and note that this 3 cross, see, until now what you saw was simply R was, which was actually a 2 cross 2, right? You saw only a cos theta, sin theta, minus sin theta, cos theta, right? But now when you actually talk about a complete camera motion, the R in general we will write it as a kind of 3 cross 3 matrix, and we will also see what when will this R reduce to that, and so on, the one that you saw, which was the in-plane rotation and so on. So this R will be a general 3D sort of a rotation matrix. Okay, this is a 3D rotation matrix, which means that, and this also involves the complete sort of a composition. Whatever order in which these rotations would have occurred, could have occurred, all that is encapsulated in this R now. Okay, and then you have a translation vector T. Now I'm moving from the image coordinate to actually the way the camera moved now. See, there when I wrote small tx, ty and all, I said that's on the image plane. That's the image coordinate motion, right? Now this T is the camera motion now. This T is because you're coming from O1, you're bringing the camera to O2 by going through some translation in the world space and going through some rotation in the world space and reaching O2, right? So this is camera translation, this 3D rotation matrix of the camera, and then you will have a 0 vector which is like 1 cross 3, and you will have a scalar. This T is of course 3 cross 1. So what this means is that your camera is actually undergone a translation Tx, Ty, Tz. I told you, no, in a general case, camera can translate along x, y and z directions. And this R will be a composition of these rotations about x axis, y axis, z axis in whatever order. Okay, and there are ways to interpret this R which we will see later. Okay, there's some very elegant ways to interpret R. And this is what we have, and then this acting on x1, y1, z1, 1. Okay, this is how we write, if we were to write in a homogeneous form, the motion in going from O2 to O1. I mean, what is its effect on the point P, right? How does its coordinate change? Okay, you can actually check that this is simply x2, y2, z2 is equal to rx plus t. Okay, that's what it will turn out to be if you simply solve this. Okay, so in this case this will be a 4 cross 4. This is 4 cross 1, and this is of course 4 cross 1. Right? That's how it is.